Well, good evening everybody, and welcome to the first talk of 2018. Before we get on to tonight's session, just to remind everyone that the next talk will be on the 8th of February, and is Pip Wilcox from the Bodleian Library, who's going to talk to us about research using digital collections, so that should be an interesting session. Move on now to tonight. Tonight's presentation is given by David Hughes from Tessella, a former colleague of mine. David has over 14 years experience as a software developer, project manager, program manager, and as an analytics strategist for a wide range of industries. A key part of David's work is actually advising clients on how to use analytics and data science to improve their operations, increase efficiency, and make successful digital transformations. He's been successful twice at the BCS UK IT Awards, with winning categories in 2014 and 16 with different projects. So he's been a recipient from the BCS. David's presenting tonight on real-world analytics and the future of data science. So over to David. Thank you.
Thank you, Ryan. Thank you, Ryan, for that introduction. Pleasure to be here on this rather blustery January day. What am I going to talk about tonight? Well, it's a sexy topic. It's something that's in the news a lot. We see AI, data analytics. It's all over. Gets a lot of press. And it's clearly something which sells a lot of copy, generates a lot of interest. What you see in the news, though, isn't necessarily representative. It's not always what's actually out there and what's being practiced in the industry. So I guess one of the things I wanted to do tonight, let's take a little bit to the step back from the headlines and look a bit broader and look at data analytics as a whole. And why we might be interested in it, why do we do data analytics, what's involved in it. Look at real-world problems. I've got one example that I'll show you in particular, we'll talk you through. But just look at in general, what are the kind of challenges involved in applying analytics in the real world. And what's the future of data science? Well, okay, I won't answer all of the questions about what the future of data science is, but I'll pick out a few areas that I think are going to be interesting in the next year or two or three. So, I'll start with a definition. With any good definition, you go immediately to Wikipedia. Actually, this one's pretty good. So, analytics is the discovery, interpretation, and communication of meaningful patterns in data. As the definition goes, that's pretty good. Largely what analytics is. But it doesn't answer the question of why are we doing this? Why do we actually kind of want to do this in industry? And I'll propose that the reason we want to do this, the purpose of doing analytics, is to turn data into better decisions. So what we want to do is take our data and use that to inform what we're going to do in the future. Analytics kind of comes in largely in three forms. You may be familiar with this, but it's kind of bring everyone up to speed on what analytics is as a whole. It comes in maybe three flavours. Some people would say four, but the simplest one is descriptive analytics. So this is using data to figure out what's happened. Okay, so it's a historic-looking process. You are taking data potentially up until now. It may be what's just happened, or it may be what's happened a long time ago, and using various techniques to develop an understanding. So to help you gain an insight on what's happened. This may be through statistics, through averages, distributions, graphs, charts, visualizations. So it's kind of helping you build insight, but it's very much a kind of a backwards looking. There's also then predictive analytics, and this is what's going to happen. So this covers things like taking your models, also creating models based on data or based on your understanding of the underlying physics or chemistry or whatever it is, to make predictions about what's going to happen next. And your third and final one is prescriptive analytics, which takes that kind of predictive side one step further and says, given all the things that are happening and given my range of possibilities, what should I do? Now, it's not quite as clean cut between those different categories, and there's certainly various blurred lines between there. But those are roughly the kinds of things that we're doing. We're looking at historic data, looking at insight and foresight. So you could say the purpose of analytics is to help predict the future. I'll just give you a kind of a very simple examples of these. I'll take the usual car analogy. A descriptive analytics might be looking at your car's average fuel consumption, or your average speed on journeys, or even looking at Google Maps and saying, well, where's busy right now, where has been busy in the past. Your predictive analytics is sort of like your advanced driver system. So if anyone's got a car where it checks whether you're falling asleep or not, there's sort of a driver alert system, and what it's doing is it's looking at the various inputs that you're making, and some of them have cameras, and kind of looking at your face and what you're doing to figure out whether you're actually kind of just about to fall asleep, and maybe do something about it, tell you that something's going to happen. So that's kind of predictive. And your prescriptive is more, this is your driverless cars, I want to get in and I want to go to there, and it's going to make all the various decisions on the route, whether to change lanes, whether to take this direction or that direction. So typically you get more complex as you go, as you sort of go down this street. So what is data analytics? What does analytics sort of involve? To my mind, analytics and data science are largely interchangeable, not completely, but largely interchangeable. And there's sort of a core of techniques and disciplines and areas which you would expect someone who is doing analytics to be familiar with, or at least some of these. It's a very, very large area that you might be looking at. It covers everything from your classical statistics, modelling, data visualization side of things, AI, machine learning, computer vision, so on and so on. So that's kind of your core of analytics. And some of these distinctions are somewhat arbitrary as well. Where would you put a system which uses deep learning to do computer vision? Is it a computer vision task, or is it a deep learning task? Or typically you'll be various combinations of this. So the distinctions sort of don't really matter. They're more of a shorthand for a bucket of techniques perhaps that you apply in this area. And it kind of has a couple of supporting parts of it. On one hand, you've got a lot of data typically. So there's software engineering, big data, potentially cloud computing. There's often tied with these things. So there's a sort of data engineering piece along with analytics. And you also, in the real world, you have the why you're doing this. What is it you're trying to achieve? What's the value that you're going to be bringing? And for that, you're looking at things like business analysis, consulting, and project management to actually deliver a thing. And you look at everything on this board, or this slide here, and you think, I don't think I know anybody who does all of this stuff. So it's not really a technology problem as such. Most of the time, in the real world, it's a team game. You need to find the right people to fit together to build your team to be able to do this. And possibly something to bear in mind if someone comes along and says, we've got this thing which solves your analytics problems. Probably doesn't. Might do parts of it, but not all of it, because it's more about people, communications, understanding what you're doing and why, and how that will bring value. Okay, how does that relate to actually helping us do some stuff in the real world? I guess the first question is what kind of problems can you solve? And the answer is loads. Anything to do with data is up for grabs. So you can a whole range of different industries, helping you find candidate drugs, helping you improve the quality of your production line, performance, speed, all sorts of different things. Analytics is being applied in all those different areas, in all those different forms of predictive, prescriptive and descriptive analytics. Primarily, I think cutting edge at the moment is around predictive. There's very few instances of prescriptive analytics being rolled out just yet, but that's sort of going to be coming up, I think. So what are your real kind of challenges around real-world problems, and what do you have to think about? The first is data. Inevitably, data is always the major issue that you've got. In the real world, your data is messy, it's incomplete. You have problems with sensors, what happens when they saturate, just getting access to it. How do you handle huge data sets? How do you sort of fill out these kind of tiny data sets that you're trying to infer information from? So data is kind of the first and one of the biggest challenges. Maybe up to 80% of your project might be spent just dealing with data issues. Another part is methods. Well, how are you actually going to attack this problem? So how are you going to think about breaking, getting insight into your data? What in your toolbox are you going to kind of start using to attack this and gain some insight? And those two, because this is the real world, we've got to bring money into this. So you've got to have some kind of return, right? This isn't a pure academic exercise. This is, I need to know that what I spend in developing an analytic solution or researching this particular problem is actually going to deliver a return. Maybe I don't know what that return is going to be until I've had a look at the data and done some work on the methods. And maybe the methods that I choose, or maybe I have 2 or 3 that I can do, but they've got different implications and they might give me different returns. So it's actually quite complicated. You need to try and do all of these things all at the same time, which is a challenge. So actually setting up your problem and thinking, okay, have I got a real thing that I'm going to attack? Is it likely to have a benefit? Have I got the data to be able to do something about it? And given that, what sort of methods do I choose to help me attack that problem in order to get the necessary benefits to actually see a return? And that might often mean that the project doesn't go ahead because there isn't a clear benefit. And other times there are. So it's a bit of this is probably one of the biggest challenges within sort of starting up a project in this area. So let's look at a real example. And it's a container ship, and unusually for a computing talk, I won't be talking about Docker. There's a real shipping issue, and it involves what happens when you put your ship in the water. And it's also biofouling. So when you get your nice, shiny, new, clean vessel, it has very minimal drag. You put it in the water, and as soon as you do that, stuff starts attaching itself to it. So algae, bacteria, they form a kind of, they start to colonize it and form a nice slime over the outside. And unchecked, that will then start leading other things to start growing on it. So you get maybe a little bit of weed, maybe you get some quite kind of heavy weed growing on this. And all this time, your surface is getting rougher and rougher and increasing the drag on your vessel. And by the time you're kind of hacking off barnacles on your boat, you might be, it's going to cost you a fortune in increased fuel, which in the shipping industry is a big deal. So the annual fuel bill for the global deep sea fleet is somewhere of the order of $270 billion. It's big money, and that has environmental impact as well. Shipping is somewhere around 4 to 5% of global CO2 emissions. Now you control the rate of biofouling, or basically you apply anti-fouling coatings to your vessel to try and stop this from happening. And if you pick the right one over the wrong one, you can potentially make a significant saving. A saving in terms of dollar value for the guy with the ship, for the environment, because you're saving CO2. Well, potentially, 9% across the whole fleet would be a, it's not trivial, right? So there's definitely a business case here, right? I've got some value to do this. Why don't we get the right one? Fouling control is very challenging. It's very difficult, actually, to understand what do I need to put on the vessel. I'll show you why exactly in a minute. But one of the reasons is that you've got an investment cost versus a potential saving. So I know that the really good anti-fouling coatings are expensive on a big ship, but I can get a cheaper one. Well, but which one's going to give me better performance? Do I listen to the sales guy who says, you want the really expensive stuff down the bottom here, that's exactly right for you? Or do I go for the lower capital cost but maybe incur kind of larger fuel costs overall? And it's quite challenging to kind of know which one to go for, or which of those many things, and there are others, or which combination to go for. Partly because there's a lot of data, right? A huge variety and complexity in this. You look at, I think there was something like 140, 150 variables or something like that you can potentially kind of include into a model. But there's some kind of clear kind of factors that kind of group together. So anything to do with your vessel, so the size, how fast it goes, whether it's stationary for any period of time, and the kind of shape that it is, all of these impact how fouling occurs, whether it occurs, and the rate that it happens. You have environmental factors, so depending on where your ship is sailing, certain areas are more risky than others. So somewhere which is nice and warm, shallow water, say sailing around the Gulf, that's really, really high in sort of bioactivity. It's a lot of chlorophyll, a lot of things will be trying to attach themselves to your boat, whereas middle of the Atlantic, it's cold, it's deep, not so much. So if you're stationary somewhere off the Gulf, that's bad news, and if you're sort of steaming across the North Atlantic, it's not so bad, you're okay. So you have, depending on where your ship goes, will depend on what the kind of risk you're going to face, and that's very hard for kind of a human being to quantify. So what we did was to put together two parts. One is a modelling part which looks at all those different factors, tries to look at pick out the key things like your vessel type, the route, and a few other key things, and make predictions about what is going to happen, what the fouling level is likely to be for a vessel for different types of coatings. And to add to the challenge, this wasn't some big system that we can call on and do some simulations for. This is something that we want to be able to work with sitting in front of a client in their offices. So we want to be able to have it on an iPad and talk to people and say, okay, well, how about this? That would be the cost for this. So it's boiling all of that kind of complexity down into some more straightforward models that you can actually run pretty much on the fly on an iPad. Don't look too closely at these because this is all made up stuff in here, but to give you kind of a picture of what kinds of things that will go into this sort of forecast. So you're looking at the end of the vessel, and you can look up that vessel from an online database, pull all its details down. Axonville International, the company that we did this with, have access to AIS data, which allows you to look at where a vessel has historically been, so you can track it around the world, and you know exactly where it's been. You can say, this is the kind of route that you're doing, and make a kind of characterise that route as being whether it's a kind of a high risk or not. And you can put various other kind of values in, and then you can work out a number of different scenarios and compare how they go. And in the scenarios, that's where you put your kind of different coatings in for the different areas of the vessel, and start putting in some of the costs, which vary depending where in the world you are. And the software will take those and bring you up something a bit like this. Again, numbers don't particularly matter, but it's a comparison of the different costs, total costs over time. So something which is perhaps more expensive initially might save you money in the long term. So if you're looking over 5 years, which is typical for a vessel to come into dry dock and be recoated, you could save. You can quantify exactly how much you would expect to save. And from that, you can then work out what the best coating is for you. And depending on what you want to do with your vessel, that might not necessarily be the best performing one. Ships get bought and sold all the time. If I want to keep mine for 2 years, maybe the cheaper one's fine. But at least it gives you a more objective starting point than just a salesperson. And as Brian mentioned, this one won the 2016 IT award. Just got to put that up there, right? Makes you feel good. Okay. So what's next for analytics? I will.
Can I just ask you about this one? Because my impression from what you've said so far is that it was all about mathematical modelling, and you haven't really said that you got the original numbers from big data.
Can I pick that up at the end? Is that okay? I'm just aware that I'm what the time is, so I'll go in the Q&A if that's okay. Okay, what's next for analytics? I'm going to pick. I've got maybe 3 things that I want to talk about of things that I think can be interesting in this area. Before I do that, I just want to make the point that I don't think any of the things that currently happen or any of the things that we currently do are necessarily going to go away. It's going to be kind of maybe more of, or the environment is going to change slightly in the way that these are implemented, maybe change a bit. So one of the things that we are seeing now with increasing deployment of sensors and industrial Internet of Things is a slide I think from Intel. This is a huge amount of data is going to start to be potentially collected. Autonomous vehicles, that's like 4 terabytes a day. You might be looking at a connected aeroplane, which might be an order of magnitude bigger than that. If you put cameras all over your factory, Intel we're talking about a petabyte a day of video data that you may want to sift through. So it's not just cars, it might be robots. So you're putting potentially sensors on everything, and this data is it's a blessing and a curse. The data might help you build a better autonomous vehicle. You can use that to help train your cars. But it's also, it has a price, right? This stuff isn't free to kind of upload and download or store. I mean, how do you get 4 terabytes data off a car?
Did you say what LIDAR or LiDAR?
So that's kind of a light-based. It's like radar, but using lasers effectively. So you can use that to create a kind of a map of, or help to kind of enhance the sort of a map of of your environment. So it's kind of a scanning laser. So your challenge is sort of, what do you do with this? And it's not just here. And I think one of the ways of tackling this is something called edge analytics, quite closely related to fog computing. I kind of prefer the edge analytics term, but it's more about moving the data, or moving the processing of data closer to where it's being generated. Because on the face of it, most data is boring, right? If I can predict what's going to happen, and the data is exactly the same as what I've predicted, I don't really need to do anything to it, right? I don't need to store it, I don't need to worry about it. If everything is going okay, do I even need to know? So one of the trends that I think we'll start seeing is more more of these predictive models getting pushed further and further down towards where the data's being generated. Whether that's maybe in this model you might have something sort of sitting in your factory doing a lot of that kind of data collection, doing some of the modelling there and pushing interesting new data up into the cloud for kind of further training. That's one thing. You might have smarts being directly put on the robots, on your cameras, and they only do, they only start collecting data, or they flag when interesting things happen. There are some interesting kind of parallels with the way kind of the human brain works in this area, but so that's one for another time.
Could I ask, why do you call it edge analytics?
Good question. As opposed to the cloud. So fog computing is sort of the other term, as in it's close to the ground rather than up in some data center somewhere. It's kind of out towards the peripheries. If you think of my laptop or your factory as being out on the edge, and some big central data servers doing the kind of big number crunching that you would typically have for big data. You're kind of pushing the little bits, it's pushing a lot of the processing kind of down towards the edge. It's just the name it's called. Okay, intelligent assistants. You'll be familiar with things like Google Home and Alexa, and they kind of that's taken off in the last sort of year or two. Not quite obvious how that sort of technology itself will I don't think I'm going to have an Alexa sitting on my desk at work, for example. But the idea of intelligent assistants, of AI being used to support you in your role, is something which has actually got quite a long history, but I think will be increasingly deployed over the next few years. Chatbots is currently all the rage. You go to an AI conference, they'll all be talking about chatbots. And if you go online and you use the online chat to switch your electricity or to ask about a product, you may well be talking to an AI bot for a while before an actual kind of customer representative drops into the conversation and takes it over. So they're kind of being deployed to field those sort of initial queries, so being like a clever search, and direct you to the right person before actually having kind of a human being kind of pop into the conversation. And they're being used for all that kind of augmentation of worker roles. I think is we're seeing that a lot. I don't know if you saw the story about movie scene selection. So a movie trailer was effectively produced by AI. Of course, it wasn't really, but what the AI did, if you have Google Photos or Google Photos, it's a very similar sort of thing. It took a bunch of scenes, like the whole movie, and it picked out what it thought was the interesting parts, and kind of gave the producer kind of a first cut of this is what it might look like. So it's not going to take anyone's job away, but maybe it gets rid of the kind of slightly boring part of I need to have about 3-minute trailer of an hour-and-a-half movie. Can you maybe, give me a first shot on that, and I'll tweak that, rather than having to do everything from scratch. And you see other things like that. So Excel flash fill is a completely different type of technology, but again, you give it some examples, and it does some clever stuff and formats all your data in the way you'd expect. I'm sure there will be more, and I think we'll start seeing kind of more specialised versions of this in industry in different sort of areas. So the kind of the technologies, sort of speech to text, text to speech kind of stuff, which underlies things like Alexa and Google Home, those are the things that will be used. I think will also start to help. And I can't have a talk about analytics and not include a bit about deep learning. It's currently all the rage, right? It's getting a huge amount of press. There was a talk last year here from DeepMind talking all about AlphaGo, I think, and I think it's shown some clear promise. It's had some success in some very, very challenging and complex areas, and it's got a lot of really smart people doing a lot of work on it, and it's developing very quickly. from would I deploy it on a system coming up soon? I don't know. It's seriously overhyped at the moment. So at some point there'll be a correction from it can do everything to, okay, these are the areas that it's actually quite good in. Maybe we shouldn't use it for absolutely everything. And there's a couple of questions that if they can be answered, deep learning will be everywhere, and if they can't, it'll maybe find its niches. So training bias is a major problem. You know, how do you make sure that you're not training your deep learning system to discriminate against certain people because they weren't in your training data set? It's a tough problem. Google's come up against this as well. You may have seen the headlines. And security and predictability. Again, I don't know if you may have seen this sort of stuff before.
May I have just a little question?
Mm-hmm.
You mentioned the rapidly developing deep learning, but the concept of neural networks, backward propagation, everything, doesn't actually much change ever since 70s.
So the core, absolutely. So it's a technology that has been around for a long time and periodically kind of is people get excited about and then it sort of falls away again. They get excited about it again. It's not so much that there is quite a lot of research. There's a lot of research going on at the moment, and a lot of papers being published in the last few years about how to kind of productionize this stuff, right? How do you actually start using it? And I'll give you an example of more recent stuff for why it's tricky. Is we don't. Part of the reason I sort of bring it up is in deep learning we still don't really know why it works, right? So we know how to build it, but we don't necessarily know. We don't really understand what it takes to make it successful, or more importantly, how to break it, or how to stop breaking it. So here's some examples. I think this paper was back in 2014. There's been a couple of different types of attacks. Effectively, these are attacks, or adversaries of examples on image recognition. So on the left, you trained your neural network on a whole bunch of different images, and it says, okay, yep, there's a school bus and a dog. Great. And then this is sort of massively magnified, but you make some little tiny changes to that image, and you give it back to the classifier and say, what is it now? That's an ostrich. Now, you and I will look at that and go, no, it's definitely still a school bus, right? But these little tiny changes have been enough to completely confuse the neural network and the output that it gives, and is incredibly hard to defend against. Partly because you can use your neural network to train the adversarial examples against the classifier. So you don't need to know anything about how the neural network's been created. You can treat it as a black box, and you can do these sort of attacks on it. So it's going to be an interesting area. I think there's still quite a lot to develop, but there's a lot of excitement in there. It'll be interesting to see how that develops. Want to keep an eye on, but also to keep your sensible hat on, I think. And with that, I will just sort of wrap up with what we looked at. So we looked at, talked about what data analytics was and why it's interesting, because you can predict the future. A bit. Looked at some real world problems, some of the challenges involved with doing that, and I didn't quite answer what the future of data science is, but we looked at some interesting examples. And time for questions, I think. Shall I pick up yours first, if that's okay, as I put you off till the end? Can you? You have to remind me what your question was, though, if that's all right.
Yeah, sorry, I've forgotten what your definition of analytics was, but I was kind of expecting you were going to be starting from
big data.
Okay.
Yes. So it was the reason for deferring is I think it is an interesting question, and it is all around what do people think of analytics, and partly it changes depending on who you talk to and what's in the news at the moment. So data analytics as a whole, analytics covers all the things from I have a tiny amount of data and I want to extract the maximum amount of information possible out of it, which is pretty much classical statistics. It might be frequentist, might be Bayesian, but it's probably you're trying to wring as much data out, much information out of a few data points as possible. And that's still relevant. It's hard to do drug trials. It's hard to do drug discovery. You don't get, it's expensive to do. You always have limited amounts of data. So that's kind of not going anywhere, but that's still analytics, and sometimes that's the right approach to take. I think has big data gone through its maximum hype? Is it coming down again? I'm not sure, but big data went through a phase of being really kind of the buzzword, and everyone was doing big data this and big data that. It's still there, right? It's supporting a lot of this other stuff, but AI is kind of taken over the buzzword maybe at the moment.
So your shipping example was based on a mathematical model?
Yeah,
of
but
data.
But if you look at, it's a huge amount of data, but actually it's not a. So the example which is in the iPad app is a mathematical model, like you might have produced, since whenever. There is the next version, the N+1 of Intertract Vision is looking at, how do I take my 4.3 billion data points? So it's all kind of part of that to produce a better model. So it's using all of the data, but what you deploy into the app is you need to shove everything onto there. If that makes sense. And a little bit like all your huge amounts of image data to train your neural network, but what you end up with is a neural network that you kind of shrink down into a little thing that you can then deploy onto a phone to do your facial recognition. Okay. Have any questions? Yeah.
David, you talked or you touched upon, I think, the human aspects and the difficulty in that area. Now, the example you gave at the beginning of the container ship, I would see that as sort of a closed system, as opposed to an open system where the factors are all sort of not predictable but knowable. So I would assume that once you bring in the human element and open systems where your factors are not knowable, that you're going to have real problems. So the question is basically, what about the human dimension?
Humans are surprisingly predictable. The human behavior have structures which repeats all the time. Statistically.
So it's an interesting question. What do you do when you don't know where to start? Pretty much, right? That's not uncommon. Actually, you go into a problem. Typically, you know very little about it, particularly if you go in as a consultant. That doesn't necessarily mean that you're at a disadvantage. A lot of the time, we see people who are well steeped in it have a particular viewpoint and a particular way of attacking a problem, which isn't helpful, maybe, or you need to think about it in a different way. So there are techniques that you can use to start attacking problems where you don't really know kind of where to start. So you typically would do things like dimensionality reduction. So you would apply things like principal component analysis, say. So you maybe go from, which is a technique of explaining away variability. So how do I make a combination of dimensions which explain the most variation? Maybe pick two or three.
Example? To what extent has there been exploration of analytics and data science with neuroscience, where advances are being made, where neuroscientists are finding more and more about how and where and why the brain works, and there must be huge amounts of data that could come out of that, and how that might be,
could be. It's not my particular area of expertise, but there was an interesting article I came across. It's kind of a review of sort of neuroscience and the way the brain works, which is kind of related to the edge analytics I was talking about. And if you look at the way, say, vision works, but actually just everything about the brain, how it works, is that the brain is basically just doing modelling. So it's not I'm seeing things, and that is triggering stuff to happen in the brain. The brain's going, okay, I've got my model of the world, and this is how everything happens. And if there's something which is surprising, that's what gets attention, until it's not surprising anymore. And that's kind of like edge on it. This is a really, really simple explanation of a very complex topic. But the way the brain works is to kind of minimise surprisal. So if there's sort of a multiple layers, multiple hierarchy of processes that happen in the brain, which effectively is doing guesswork about what's going to happen next. Right? So what am I seeing? Is it a cat? Is it a dog? Is it a car? It's a car. Okay, well I expect to see doors and what, probably not going to be pink. Oh, it's a pink car. Maybe that's a bit surprising. Okay, but it's still pink, so it's not changed. There was a good experiment, which I will struggle to remember the details of, but effectively, if you show, close off someone's vision and show them one picture in one eye, one picture, completely different picture from the other eye, maybe a cat and a dog. Each eye can only see one or the other. What would you expect to happen? What would you expect to see? If I showed you a cat on one side and a dog on the other, what would you expect to see? I think before I read this paper, I think, well, you'd see some kind of blurry combination of sort of cat-dog thing, right? Not really clear. What you see is a cat, and then a dog, and then a cat, and then a dog. And it doesn't settle down. You keep seeing one or the other. And it's thought to be related to this, the idea of I've got a model which is saying, in front of me is a dog. Okay. The eye that's now seeing a dog goes, yep, that matches what I think is in front of me. And the eye that's going, hang on, I'm seeing a cat. This is completely different. And it waves the flags, and your brain goes, oh, okay, I'm seeing a cat now, so it makes a cat model. And then the other eye goes, oh, hang on, no, that doesn't match what I'm seeing. I'm seeing something different. And you get this sort of, so not my particular area of expertise, but kind of interesting on that's the way the brain works, or the way human brains work to kind of deal with huge amounts of data, is it guesses what's going to be there, and if it guesses right, just filters all the other stuff away. It's only things that's interesting, that's an anomaly, that shouldn't happen, that kind of gets our attention and makes us sort of, think about what that actually is.
So do you think there's potential in that area to marry those two?
Absolutely.
As a contribution, to add an example of very ancient data analytics, many decades ago, some bright guys in stockbrokers discovered that retail investors make their investment decisions about 70% of the time wrong. So most stockbrokers have a little statistical department that follows the retail investors called the cattle statistics group, where they follow decisions, they do simple tracking of the investment decisions, and they do the opposite. And another little thing. I've seen other papers on those fooling neural networks things, but one of the things that amuses me when I saw them is that there is a thing called the optical illusion competition in the world, and it has a Wikipedia page, and when you see the optical illusions that fool like the dog and cat one, our own neural networks, one gets pretty worried.
Actually, it's a simple question actually about when you're explaining your idea of future analytics to potential clients and projects. That are they expecting something out of a black box? That you show us a very elegant international application, and you think, okay, yeah, I can see where that's going. And then you look at all the various other categories that you could bring to leverage, like AI. You think, is it going to do something smart? But are you not going to know for 5 years until it all comes back and it tries to learn better? How do you set an expectation of what all these advanced technologies can do and bring to the table? How do you set an expectation?
I think it's a very good point, a very good question, and a challenge. So we, as Tessella, we have a kind of a methodology that we can use and a way of guiding people through effectively a set of stage gates, right? So you kind of look at it at an early stage and say, well, is there even a project here? Do you know what you actually want to do? Do you have an end product which is going to save you money, or what's the size? There's no point us spending a year doing something if you're only going to save $10,000 a year, right? There's just no point in doing it. So there's that kind of, do we have a product? And then you look at the kind of prerequisites. Like, have we got data? What are the expectations? How accurate do we need to be? So there are some projects or some problems will be quite straightforward, or quite good tolerance for false positives, false negatives. As long as it's a bit better than we can do as humans now, maybe that's good enough. Okay. Others maybe not so much. You probably don't want to have an alert on your aircraft as it's flying over the Atlantic, which says your engines are about to fall off when they're not, right? Or vice versa, that everything's okay, go and take off on that and have your engines explode. So depending on where you are, that will constrain the kinds of models that you can use, the kinds of approaches that you can use, and how expensive that's kind of likely to be. So it's one of those where it is a little bit of a process of discovery, but you can have points along the road where you say, okay, this is what our understanding is right now. This is where we would go next. And you see, it's kind of it's both iterative, but you can put stage gates in there and keep expectations sensible. So it's not a case of we've got this technology and we're going to apply it all over the place. There are companies that do that. Here's our AI, and it's just going to process your data, and away you go. This is more about what's right, and the right answer might be, well, we spend a week in MATLAB or in Excel, and there you go, right? Is that good enough? Right? Oh, we need it a bit more, and we'll save more money. Okay, well, let's do a more sophisticated model and take it to the next level. So it's much more. That tends to be much more collaborative and much closer to it's the teamwork aspect that I think is key, and working out what it is that what's really going to benefit the client, what's really going to kind of deliver value.
Is it reasonable to expect the unexpected, because you're using tools that probably the client doesn't know what they're capable of, and hence won't know what's going to come out of them?
Yes.
So you have things that international didn't ask you to. And say, well, I should have never thought about that because we couldn't look at it like that way before.
I think that happens quite a lot. You see that quite a lot as a consultant, where you're in certain industries where certain approaches are kind of taken for granted, and you go into a slightly different one and they have a different set of approaches. But you go, well, that problem actually looks like this other one over here. There's a great example of this, actually. One of my favourite ones. It always brings a smile to my face. So we did some work on the Samson radar on Type 45 destroyers. I'm familiar with it. So it's a really powerful radar, and the idea is that it can track lots of different things. And the way that radar works is you get a kind of a sweep. So you see, you get a track, and then you get another sweep later. And so you've got to kind of match up where these objects are, where they've been going, what's happening. Turns out, if you want to track regrowth of armpit hair, you can use the same sort of approach. So you get a consumer industries giant was looking at hair removal cream, how effective it is, and once you put it on, you then take pictures of the armpit and sort of see how quickly the hairs regrow. It's the same problem. You've got snapshots and you're trying to reconstruct, is that the same hair or is that a different hair, and how so and you can use the same, you borrow that kind of tracking technology from something that was used on radar tracking and use it on armpit hair. So unexpected, yes, unexpected reuse. But again, it's all kind of mathematics, and you can use it in lots of different ways. It's maths.
I think there's a lot of flexibility. There's a whole amount of tools to pick from, and you're never quite sure if you're only used to say Excel or just one way of thinking. But actually, by leveraging these in different ways, you will actually come up with slicing and dicing in a way that you wouldn't otherwise be able to, and hence got answers you wouldn't have expected.
If I can comment, if you want to do some analysis, you usually start with dirty prototyping. You just try to find something, and then maybe you use better tools. And
I think it's tool. Yes, so you start small and you start in ARM. Yeah, exactly. Yeah, and you do some stuff. But what you're doing is also, where do I start? Do I start with a linear model? Do I start doing Fourier transforms? Do I start with PCA? What is it that and that is it's problem dependent, and it's a lot of judgment, a lot of experience, and a lot of judgment. People who've done it for a long time, and maybe multiple people looking at it with different opinions, and you try so out cheaply. If you've got something like R and you've not got someone who knows about this stuff, you can explore a number of different options quite quickly on maybe a subset of your data, and then if it looks promising, you then sort of push out and you continue to develop.
How do you decide whether a mathematical modelling approach is going to work versus a sort of a deep learning approach? Because you sort of alluded to it earlier, saying that with a deep learning approach, you don't know what it's doing, it's a black box. Whereas if you're doing mathematical modelling, you're devising the mathematical models which will be applied to work out the solution going forward. How do you decide which one's going to work?
Some of it is a little bit of experience and judgment. I've seen this kind of problem, or I've seen this kind of stuff before, and what worked was this sort of approach. So that often informs your starting point. The other is there are certain techniques that you can do which help to kind of narrow down. You can look at all the time. You're looking at is there a signal here? Say, right. So can I depends what I'm trying to understand as to what kind of approach that you use. Sometimes you might have a good starting point. Maybe it's a physical process. You might have a good starting point of, I kind of understand something about the physics that's going on. Maybe I know there's a cubic, relationship with something. That won't explain all of it. Maybe that's a starting point. So I'll put that in my model, and maybe I'll separate out different chunks and see if I can explain some of the variability in different ways. It's not straightforward, and how you go about sort of slicing and dicing your problem is hugely context dependent. But I say, rarely do you go in knowing nothing about it. Sometimes you're going, well, I'm not going to create a self-driving car using a linear model. Pretty sure about that, right? So that's the kind of thing where deep learning is. It's like I don't even know where I would start in trying to build a model to do a car in a busy environment. You might be able to do it for on tracks or kind of a guided busway kind of thing, but not for an unpredictable environment. There you're looking at that kind of AI approach, or the sort of deep learning type approach, but it's very difficult to know when you're done. That's the problem that the automaker is going to find, is that they're kind of maybe 95% there, but that last 5% is going to take longer. Going from 95% to 96% done is hard, but going from 98 to 99 is going to be really hard. And we'll see if they ever get there, or whether it's always just not quite good enough. And then you get someone who sticks a sticker over your 30-mile-an-hour limit, and it fools your car into thinking it's a stop sign or something. It's a different issue.
I want to object a bit to the question, because it was putting a distinction and a position between two things, but they're actually three things. There is another approach in the middle, which is exploratory data analysis. That is, you assume you can do a model, let's say, in your head, or you feed data to a neural network and somehow it comes up with matches. But in the middle, there is also programs that try to analyze the mass of data and find systematic relationships in an analytic way. That is pattern cluster analysis, essentially. So some of them, I have read about some of them, and some of them can reproduce physical laws. I can't remember an exact example. It's like if you put in one of the systems the data of all the orbits of the planets, it will come up with Newton's laws or similar things. And they're fairly well used. But
the other part of it is actually you will use your descriptive analytics part. Right? You'll take your data and you'll plot it out and you'll have a look at it. You use the Mark 1 eyeball and the Mark 1 brain and go, well, is there something in here? Can I, where might I start? That looks interesting. Is that a thing that I want to have a look at? Does that explain away enough? It's incredibly useful. Descriptive analytics is incredibly useful for just getting that handle on a problem. Is almost always where you would start. You give any of our analysts a bunch of data, and the first thing they'll probably do is plot it out, see what am I dealing with? Is it really noisy? Is it quite smooth? Is there seasonality in there? So you start kind of chopping up different dimensions, looking at different aspects of it. Then you have a range of models maybe, and then you narrow it down based on how they perform.
I like the concept of smog computing, and I'm wondering how you engendered trust in this area. If I was a snake oil salesman, I'd use your carbon call thing to sell my snake oil, because no one really understands what's happening in your black box. It's also fairly certain that the reason we had the financial collapse in 2007 was because all the financial engineers sold the bosses of the banks snake oil. And none of the bosses of the banks understood what the financial engineers were doing. So there's huge issues here about accepting as fact things you don't understand how they're being worked out. How do you get over those hurdles? Or should it be a criminal offence to do that?
Well, fortunately, I'm not in the business of selling black boxes, so I can say it's clearly a terrible idea to do that. You want to employ people? No.
It's very similar to black boxes, isn't it?
So the idea. So a lot of the time, it might look. We do here might look complicated. It might be quite simple. I mean, those models that you've got on the edge might be quite simple, sort of linear models, or it might be some combination of things. I think maybe the interesting part is when you've say in a manufacturing process, you've got a range of tolerances for your end product. And each machine probably has a range of tolerances that machine, the part that machine will produce. But you're kind of, if everything, what's interesting is not necessarily whether a piece of machinery is within tolerance or not. It's has it changed? Has something happened which suddenly now this part is now being produced a bit slower than it was. Is that cause for concern? The cycle time's gone up slightly, or the temperature that this machine was running at is still within tolerance, but it was kind of nice and stable, and now it's sort of just jumped up a little bit. Do I need to do something about that? And if that relates to some other part of the network or something else which has changed at the same time, having a system which is sort of looking at, well, that's a bit different and that's a bit different, and doesn't necessarily, it's not automatically going to shut down your production line, but it's maybe going to flag to a quality engineer, maybe there might be something going on here. Or just to, again, every part of your system is sort of working within tolerance, but a combination of these errors sort of accumulates in the wrong way and starts giving you kind of issues. So putting kind of smart stuff, I'm not thinking really of an AI in the form of a kind of deep learning. I'm not sure what's going to come out of it. Just do some magic things. It's much more on. We see these sorts of patterns across the factory. Is that a problem? What do I want to? When do I flag an anomaly might be happening, or I might need to go and look at this particular piece of machinery.
So there's still a place for common sense.
Absolutely. And that's kind of why I see that it's not replacing humans. So this sort of AI, not replacing humans, but enhancing them. I don't want to have to look through pages and pages and pages of reports which have temperature, which is all the same, or even particularly I don't really want to have to look at graph day after day after day and see what it is. I want the system to go, I think something interesting is happening over here, or there might be a problem. So that kind of removing the relatively simple filtering or kind of that first pass, going, this is stuff. It might then, you have the risk of you create blind spots because people aren't looking at this stuff anymore, but by and large you can, as long as somebody is looking at the data, if it helps kind of filter it much more quickly, then that's you can be a lot more effective in your role. And that's a thing that that we can see already happening, but will continue to.
I would have a question.
Yep.
As there was experiment when they put basically two deep networks speak together, and they created encryption because the code mission was communicated in the way that the middle machine cannot understand what they speak. They created encryption which worked. You can analyze, you can see how the neuron weights are set. But is there a way from the network weights to extrapolate how it works?
I don't know. A short answer. It's not my deep learning in particular is not kind of like my area of expertise, but it's. I know that there is a lot of work going on to try to help understand what's happening in neural network models. It's currently a kind of a weakness. Is that you can look at the network and look at the weights that are on there on the nose and what have you, but you can't get an understanding really. It's hard to generate an understanding of what's going on, what's it looking for, what are the kind of features of interest that it's actually picking out. And there's quite a lot of work going on in that domain to try and understand it. So that's kind of why I think the area is interesting, and will be. I'm kind of hopeful that at some point we'll be able to understand it in a way that we can kind of trust it. Have a really thorough understanding of this. This is what's happening. This is why it's happening. Okay, good. We can kind of use this. At the moment, it is a little bit kind of black box. We're not quite sure how and why it breaks, or we're still kind of exploring it, I think.
In your ship Valley example, presumably that wasn't a sort of AI type model. It was some sort of statistical model based on the data.
There's a kind of a number of different models kind of combined together to look at different aspects of it. So, the relationship, say, between the average hull roughness and power is one that's sort of quite well established. So that's sort of in the literature you can pull that out. Looking at how the size of vessel changes, the power and things like that. Again, that was something I think needed to do some computational fluid dynamic modelling for. Other ones were around, the kind of your kind of algae and the biological side of things, and that's kind of another model again. And you can a lot of the time you can separate out the different little components and then sort of bring them together, rather than here's all my stuff, let's chuck it all into a kind of a black box and see what comes out. I mean, it's not it is pretty good, it's pretty accurate. There's more things. There's always more stuff that you can do, right? You can always make it kind of.
I guess the question I was getting to was, once you've got that model, and you decide to code the ship with whatever, and then you measure that, do you then feed that back in to improve the model, as it were, or just by sort of tweaking the parameters, or do you actually have to sort of rip the model apart and say it's different?
I think in this case it's more that there are certain simplifying assumptions that were made in the creation of the model, and that what we produce out of it is good. But you also know that it's like if there are going to be areas where it's like I had to make a simplifying assumption here. Ideally, I will go back and I will fix that, either with more data or more research, or it's just a bit more time spent on separating out what I've kind of combined together in a single factor into a number of different ones. And some of that might be because there's data that is needed, or it's just a better understanding of what the difference is between that kind of bit is. So, I mean, the kind of the sort of biology side is probably the one that's the most complicated. Physics is, in some ways, CFD is hard, right? But it's it doesn't sort of tend to change depending on where you are in the world, whereas, you know, plankton and algae and bacteria and stuff, it does, and they all have their own particular characteristics. That bit's kind of the challenge, I think.
Any more questions?
Well, sorry, I had a concerns about your container ship example again.
Okay.
So, as I understand it, you were making predictions about savings.
Yes.
So, I guess you have a couple of years of data now. So, has it been validated? And then the second one is, when you make the predictions, presumably you must have had some error bars on there. So, I didn't see that in your plot. I mean, there just seem to be absolute numbers. Presumably, they must have asked for some error bars on your
So
predictions.
that's a good spot, and I'll answer that second question first, which is actually what I showed you one of the charts that it produces. That is the sort of the 70% expectation.
Yes,
So
P70s.
out of 100 ships, 70 would be around that level of performance. You can also generate a 20% and 10%. So occasionally stuff happens. This is a lot of this is based on AkzoNobel have a huge amount of historic data. So what happens when a ship comes into dry dock is that they do an inspection report and they look at the fouling on the vessel, corrosion. So they do all sorts of take pictures now, but they've actually got 30, 40 years or more of data that's sort of been gradually accumulated, and that is a sort of a gold mine for doing this kind of work. Pull that kind of information out. So they know, given certain coatings and certain vessels and where they've been, what kind of performance, what kind of real world performance they get. So they've actually always been collecting that data, and they've been sort of validating the models against kind of the actual kind of performance. But equally, events happen. It's very hard. You can't, unless you get kind of sister ships that are on the same route. It's very hard to actually know whether the predictions that you made were wrong because sort of something happened. Maybe it was shoved out of port by a particularly poor tugboat driver that scrubbed a big hole in the side of the coatings, or they scraped it along the the Panama Canal as they were sailing on, and that's caused some issues, or just they happen to be unlucky. They've anchored up at this point rather than this one a bit further down the coast, and it happens to be somewhere which is particularly bad choice or good choice or whatever. So there are significant error bars on there, but the overall kind of results have been validated against real vessels.
I have a question on this now. You said that you have 40 years of data basically. With this amount of data, what leads to the decision to use modeling instead of neural network? Because with this amount of data, I can imagine that the neural network would provide quite good.
You might think so, yes. Part of the reason is what we discussed in terms of the sort of the weaknesses and some of the kind of chucking everything at a black box and seeing what happens, because that understanding of how the model works, that kind of confidence in the model, is actually a key part of it for the customers. Right? If I'm going and presenting this to the customer and go, okay, this is just, we set a machine guide on this and it came up with this stuff. Right? Really? How? What's going on? What are the key? What are the actual driving factors for this? I don't know. It's kind of magic, right? Who's going to trust you? No one's going to believe it, right? We're like, yeah, I'll take a pass, right? But if you can explain, what's actually been done and what the kind of key parts are. The other is actually the data. You've got a lot of data, but it's not always. It's not in a nice kind of form. It's not a nice sort of simple. I'm going to put this in and I trust it, because it kind of depends on who was doing the report. A lot of it's textual or it's pictures. Certainly going back, sort of further back, it's more about reports. So someone goes, it's about kind of 10% fouled. Another person might come along and go, well, about 15%. They're not really measuring it. It is kind of a lot about judgment. So taking a human interpretation of the data, you can kind of deal with that. If you just it actually would be quite a lot of work to kind of tag it up in a way which was kind of consistent. I think there have been machine learning approaches taken on that data, which kind of wasn't used for this, but it's for this one in particular. It was actually making sure that you understood the model and could potentially explain it to clients about how that's worked and have the confidence that to be used to that it needed that to be able to kind of deliver what it set out to do.
Well, I guess if there's no further questions, it just leaves me to thank David for his talk tonight and giving us an insight into how difficult some of these problems are, and perhaps adding a little bit of reality to some of the hype we see in the newspapers. So thank you very much, David.
Thank you.